Hi everyone, my name is Alex Krotz, and today we're going to talk about fluorescence. You might already be familiar with glow-in-the-dark materials that absorb light during the day and re-emit that energy at night in the form of light that we can see. Fluorescence is similar, but occurs on much faster timescales. Today, we'll discuss some examples of fluorescence, and also why it happens in some systems and doesn't happen in others. We'll also discuss some potential uses for fluorescence.
Here I have some of the materials we'll be using in our experiments today. This is an ultraviolet lamp. Ultraviolet light is a color, or rather energy of light, that we can't see with our eyes. It is emitted by the sun and makes its way down to Earth, where it can cause sunburns, snow blindness, and in some instances, skin cancer. It's important that if you decide to repeat this experiment at home, you take precautionary measures against these harmful effects by wearing long-sleeve shirts and wearing sunglasses. I'll be taking these measures behind the camera. In the camera, you can see two white materials. On the right is a sheet of copy paper. On the left is a sheet of foam. Under the light of the room, they both look pretty much the same color. The light of the room consists of light from a CFL and very little sunlight. When I turn on the ultraviolet light source, however, you can see that the copy paper is suddenly bright blue and glowing. And the foam has a color that has remained relatively unchanged. Also notice that the black of the table has not really changed either. This is because the copy paper has been embedded with a fluorescent material. That fluorescent material was bonded to its fibers when it was made. It's not natural, or this is not a naturally occurring phenomenon in paper, but is rather a commercial tool used to make the paper look brighter than other non-treated papers. Here, I have a small cap full of laundry detergent. Now, on the paper, the laundry detergent doesn't really look like it's fluorescent. But this could just be because the paper is fluorescing so strongly. So let's take a little bit of that laundry detergent and put it on the foam. Instantly, you can see that the laundry detergent is fluorescing as well. In fact, on the surface of the foam, it creates a bright pattern where I spread the laundry detergent. Now, when I rub the laundry detergent, or when you wash your clothes with the laundry detergent, some of that material remains in your clothes and makes them look brighter than they would had you washed it with just a soap.
Let's discuss some of the results we've seen so far. We saw copy paper, which was embedded with a fluorescent material, glowed brightly under the ultraviolet light, while the foam, which was a similar color under the ambient light, didn't glow at all. We also saw that laundry detergent, which we posited was also filled with a fluorescent material, glue strongly, even when it was spread on the non-fluorescent foam. This is because some materials exhibit the property of fluorescence and others don't. Why might this be? To explore this concept, let's look at a non-fluorescent material.
So let's see what happens to this leaf when we turn on the ultraviolet light source. As you can see, the color hasn't really changed. Here, I'll turn it off again. To make that even more clear, this is a small vial, or a small capful, of chlorophyll. It is the exact compound that is present in leaves. As you can see, if I take some of it and I put it on the paper, the fluorescence of the paper is essentially damped. That's because the chlorophyll is utilizing that energy, or rather absorbing that energy, and not re-emitting it. Now, let's see if we can explain how that process works. Here, I have a diagram of a two-level system. This is the ground level, on the ground, and this is the higher energy level, the chair. This ball represents the system that we're considering, or rather the energy of the system that we're considering. Incoming light comes in and excites the energy to the higher energy level. However, this higher energy level is unstable, and perhaps it might decide to decay. Oh, just decayed back down to the ground state.
So as we just saw, fluorescence requires two processes to take place. The first is an initial absorption of incoming energy. This we saw in the form of the ball being excited from the ground state on the floor to the excited state on the chair. Second, that excited state has to decay. That we saw in the form of the ball being dropped from the excited state back down to the ground state, resulting in the release of energy. The key difference between fluorescent and non-fluorescent materials is that in fluorescent materials, this decay results in the emission of a photon of light that often we can see with our eyes. In non-fluorescent materials, that energy is used, or dissipated rather, in a form that doesn't emit a photon. In plants that utilize chlorophyll to do this initial absorption, that energy is transferred to the chloroplasts to execute photosynthesis and make food for the plant. The reason that we used ultraviolet light was to provide enough energy for this initial absorption to take place. If we don't provide enough energy, the ball might not make it to the excited state level, and so no fluorescence will occur even if the material is fluorescent. That's why under wavelengths of light that are lower in energy than ultraviolet light, like red light, we don't observe a glow. Thanks for watching my video, and I hope you learned a little bit more about fluorescence.